So I want to touch on a question in the unit review. This is like the unit 2 review. See if I can get this going here for us. So this is the unit 2 review. I think this is question number 28. So this is from, I think, section 4.2 dealing with binomial distributions. And I'm going to show you how to maybe set this up using a calculator. So we have 72% of adults live at an age of, want to live to an age of 100. So you randomly select 5 adults and ask them whether they want to live to age 100. The random variables are represented by the number of adults who want to live to age 100. So it completes parts A through C. So I'm going to attempt to do part A in this problem, and I think you may be able to figure out the rest of this, but we'll see where this takes us here. So what we want to do is conduct a binomial distribution. And remember, a binomial distribution can be done using the calculator. So notice how we have to do 1, 2, 3, 4, 5. There's 6 of these guys that we want to do. So to construct a binomial distribution, we have to evaluate each one of these. So notice how if we go to, I think it was second VARs, right above it is the DISTR button, that's distributions. If we hit like alpha and then A, that actually takes us to the binomial probability distribution function. So if I do that, that kind of takes me straight there. So the number of trials, I believe we had 5 adults, so we have 5 trials. The probability was that 72%, so we have to put that in as a decimal, 0.72. And the first 6 value is nobody wants to live to the age of 100, so I can't imagine people saying no to that. So if I put 0 in there, hit enter, it'll tell me to paste. So this will now do the actual formula that was in the book. And we end up with this number 0.0017. So our directions say 5 decimal places. So that's going to be like 0.0017. And do we keep the 2 or do we round it up? Well, since there's a 1 after that 2, that means just to keep the 2. So 0.00172 would be the probability for that. So that's not even really, if you move the decimal over, it's still like 0.1 or 0.2%. So not many people. So if I want to do the binomial distribution for one person, doing that. So if we do that, again, we can do second VARs for distribution. Hit the alpha button and hit A, that'll take me to the actual function. We don't have to change the 5. We don't have to change the 0.72, but the X value has to change now to a 1. Hit enter, and then hit enter again. So that gives us our percentages there. So that's going to be like 0.0022. And do we keep the 1? Yeah. So we do keep the 1 there for that one. So if I want to do now the 3 or the 2 rather, we do the same thing. Second distribution, alpha A takes me down to where it is, 5.72. This has got to change to a 2. Hit enter, paste, hit it again. So now we end up with, and yeah, it's starting to kind of jump up because I would think most people want to live to the age of 100 if they can. Some people have the reasons not to. So notice how it has a 3, 7, 9, and then there's another 9 though. So that 79 is going to have to round up to an 80. So this is going to turn into, instead of 79, we'll have to round that up to an 80. Let's see if I can find my eraser. So we got to round that on up. 0.11380. So this one, since our 5th place was a 9, we round up from 79 all the way up to 80, so it becomes a 0. All right, so let's do with, that was with the 2, let's do 3 this time. So again, if you don't want to do alpha A, you can just scroll down and notice how it says A is the binomial probability distribution function. So that's why I'm using alpha A, is because that's the hotkey. So if I hit enter there, my trials is still 5. My probability is still 72%. This value now changes to 3 people. Come on down to paste, hit enter. So notice that it jumps up to like 29% of the people. So 0.29262. And we do keep the 2, or do we not keep the 2? 0.29262. But notice how there's a 6 after that too. So that 2's got to round up to a 3. So 0.29263. So that's for 3. So now if we go again, second distribution, alpha A, go down to change that to a 4, hit enter, paste. So it gives you kind of a 0.37623. And since there's a 3 after that, that does stay as a 3. Okay. And then let's do the 5th one. So second distribution, and shortcut is alpha A. That stays 5 trials, 5 people. And then paste it on down. And they'll say, well, not, it kind of drops from there. So not everybody's all in. So it drops down to 0.1934. And that 9 does stay. So that would be my binomial distribution from there. So 0 people would be 0.00172. 1 person would be the 0.00221. And again, if you want to do percentages, you'd have to actually move the decimal over 2 places, so right to actually see percentage math there. So that kind of does the table. So let me pause here for a second and see what else we have going on here. So looking at my work, it looks like on the second one there, I kind of read the calculator wrong. That should have been 0.02213. So that's a trick you have to watch out for, is making sure you write down from the calculator correctly, and I didn't. So that should be the correct numbers now. So from there, we're asked to identify the histogram that goes with that. So notice how 0, when x is 0, we have like 0.0017. So we know that's really small. So that kind of matches the first graph pretty good. 0.02, that still looks pretty good. Then we have like 0.11. So 0.11. Can't really tell on that so much. 0.29. So notice that those are not matching really well. So let's go over here, because going from the second to the third, it looks like we should be like let's see, 0, 1, 2. Let me put a 0, 1, 2, 3, 4, 5. Match those up a little bit better. Looks like 4 is the highest one. And so from the graphs, it looks like D shows 4 the highest. 3 is the second highest. D is matching that up pretty good too. So I would say the histogram that matches that is probably D. So that should match up there okay. Let's see. So the next question was describing, since D was the correct answer, is it skewed left? Is it somewhat symmetric, or is it skewed right? Remember, the skewed part is what we call the tail. So where the tail is. So notice how the tail of the graph is to the left. So it's going to be considered skewed left. It's all about, consider the high spot the head and the low spot the tail. And so since this is kind of leaning more from, it's heavy on one side or the other, this is not symmetric. But when it comes to skewed left or right, it's always where the tail is. So I look for the lower end, and that's the skewing. So that would be D, where the skewed left would be the shape of the graph there. So lastly, we have this drop-down menu, the values that would be considered unusual because the associated probabilities are, remember this 0.05, to be unusual, we have to be less than this 0.05. So if we're looking at percentages, or I guess in their decimal form, which ones are under 0.05. So if we look back up at the probability distribution, notice that 0, that's 0.00. So that is under 0.05. And notice that 1 is also, that's 0.02, and 0.02 is also smaller than 0.05. But after that, 0.11, 0.29, 0.35, 0.19, those are all greater than 0.15. So there are some unusual ones. That's 0 and 1. So you're not expected, if you're asked to live to 100, most people would probably say, yeah. And for 0 to happen there, that was unusual. So 0 and 1 would be unusual values for that question there, that 0 people or 1 people would consider not living up to 100 years of age. So that kind of concludes this question here. So hopefully you found using that graphing calculator a useful tool to kind of do those calculations.